Okay,
Yes.
great. Yeah, so good morning, everyone, and thanks for the opportunity to talk to you all about my research. I gave a talk here not too long ago, I think last March, and I was very happy to be invited back. I didn't want to overlap with last year's talks, so I've decided that I'll focus on some of the new things that my group is learning about how we can use Rayleigh waves to better image the lithosphere. So some of the work that I'll show you today has been done by two of the PhD students in my group, Anand Hariharan and Jordan Babikoff. So my title references new approaches and challenges. And the new approach I'll focus on isn't really new, I suppose, but it's a local amplification of Rayleigh waves, which is, I would say, not yet widely used for imaging the lithosphere. And so my group is studying its sensitivity to elastic structure, and we've been estimating amplification for Rayleigh waves at US array stations in the contiguous US as well as in Alaska. So I'll show some in progress results for that. The challenge that I'll focus on today is the fact that higher mode or overtone Rayleigh waves can arrive in the same time window as the fundamental mode Rayleigh wave, which introduces bias into measurements of the fundamental mode. Overtone interference has long been recognized for love waves as a problem, but the issues for Rayleigh waves are of a different nature that we only recently recognized. When we teach about the lithosphere in introductory level geology classes, it's typically described as a rigid layer that is able to move on top of the weak asthenosphere beneath it. And we teach that the tectonic movements of the plates are responsible for most seismic and volcanic activity on Earth. The topography of the Earth's surface, which is plotted here, is also a consequence of lithospheric motion. The seafloor grows deeper with time as the oceanic lithosphere grows thicker and denser. And of course, mountain ranges on continents record evidence of plate convergence. What is fundamental to plate tectonics is this notion that the weak asthenosphere accommodates the movement of the stiff lithosphere. However, what is not as clear is what are the physical or chemical properties of the lithosphere that make it stiff relative to the plastic asthenosphere beneath it. In other words, what controls its viscosity? And there are several possibilities. This figure on the left by a paper from Hirth and Kolstad in 1996 illustrates two of them. Plots strain rate as a function of inverse temperature for samples of dry olivine as solid symbols and wet olivine as open symbols. The samples were deformed by dislocation creep. And then both the data and then the flow laws that are plotted behind them reveal the role of temperature. At a constant stress, a higher strain rate is achieved at hotter conditions. Furthermore, at a given temperature, the wet samples strain more easily than the dry samples. So in other words, olivine viscosity can be reduced by raising the temperature and elevating the water content. A third factor is partial melt, which is shown on the right. McCarthy and Takei showed that even a small amount of melt can reduce viscosity by a factor of 30 or more relative to a truly melt-free sample. So in addition to temperature, water, and partial melt, other factors can affect viscosity, for example, grain size. None of these factors can be measured directly for the Earth. Rather, they must all be inferred indirectly, and seismology provides some of the best indirect measurements available. The panel on the bottom here shows the speed of seismic waves at a depth of 100 kilometers below Earth's surface. And comparing the maps of seismic velocity and surface elevation exposes certain obvious relationships that have been recognized for decades. For example, in the ocean, mid-ocean ridges are characterized by very slow velocities, and then wave speed increases with seafloor age. The old and tectonically stable parts of continents are characterized by the fastest velocity at 100 kilometers. For example, the Slave Craton in Western Canada, the Yilgarn Craton in Western Australia, the West Africa, Congo and Kalahari Cratons in Africa. On the other hand, tectonically active parts of continents like the Western US and also the East African Rift exhibit very slow velocities. So seismic velocity is controlled by many of the same factors that control viscosity, temperature, composition, partial melt, water. So velocity should be and has been an important source of information about what makes the lithosphere the lithosphere. For example, numerous studies have tried to estimate the thickness of the lithosphere from seismic velocity. This figure from Steinberger and Becker compares several of these estimates. And you can see that there is decent but not perfect agreement between them. And one reason for the differences is that there's not really a consensus on which seismic proxy should be used for mapping the base of the lithosphere. Should it be the depth to a certain value of shear velocity, or should it be the depth to the low velocity zone, or should it be the depth to some value of seismic anisotropy? Each of these choices can be justified, but each gives a somewhat different result. So I wanted to give two examples of what I think are outstanding questions about the lithosphere that could potentially be addressed with new constraints on Rayleigh waves. So this is to help motivate the somewhat more technical work that I'll discuss today. And the first example is from continental cratons. So cratonic mantle xenoliths provide some indication of what the temperature structure is like in the cratonic lithosphere. And on the left, the black symbols show temperature and pressure determined from xenolith thermal barometry from the Slave, Kalahari, and Siberia cratons. And then I've calculated two geotherms shown in red for reasonable values of surface heat flow and crustal heat production. You can see that they bracket almost all of the xenoliths. I'm also showing a third temperature profile here, which is temperature for 25 million year old ocean, beneath 25 million year old ocean floor, calculated using a half space cooling model. And all three temperature profiles intersect the adiabat at various depths. And then on the right, I have converted these temperature profiles into isotropic shear velocity using the parameterization of Jackson and Fall. So there's two main features I want you to notice in these velocity profiles. First, higher temperature maps into lower velocity as expected, and you can see that just by comparing the temperatures at 100 kilometers with the shear velocities as 100 kilometers. And second, all three of the predicted velocity profiles contain a distinct velocity minimum at about 75 kilometers depth for the oceanic profile and 150 to 250 kilometers for the two continental profiles. This low velocity zone corresponds to the base of the conductive layer, beneath which temperature increases only very gradually with depth. Now, the other profiles on the right here, the blue, cyan, pink, and green, are shear velocity measured from real seismic data at 4 different cratons: Slave, Yilgarn, Hudson Bay, and the Baltic Shield in Europe. You can see that they're actually fairly different from what we predicted from the temperature profiles. One, they contain constant velocity or even increasing shear velocity in the uppermost 200 kilometers. Second, they lack a really prominent low velocity zone that we can see in the predictions. Third, they're slower, a bit slower than the predictions at depths shallower than 100 kilometers, and then faster than the predictions at greater depths. So our simple predictions of what shear velocity in the cratonic lithosphere should be don't match the observations, which suggests there's something fundamental about the seismic structure of cratons that we do not yet understand. The second example is from Oceanic Lithosphere. On the left, these are figures from the 1992 paper by Stein and Stein showing surface heat flow and seafloor depth as a function of seafloor age from the Northwest Atlantic and North Pacific Oceans. Both quantities clearly evolve with age. Surface heat flow gets lower and the seafloor gets deeper. The long dashed line are the predictions of the half space cooling model. And you can see it does a reasonably good job at younger ages, but for seafloor older than 70 or 80 million years, it predicts depths that are greater and heat flow that is lower than what's actually observed. And so the plate cooling model was developed in order to better fit the heat flow and bathymetry data at all ages. The figures on the right contrast isotherms as a function of seafloor age for the half space cooling and the plate cooling model. As you can see, the plate cooling model prescribes an isothermal lower boundary that prevents the cooling from continuing indefinitely. So it limits the thickness of the thermal boundary layer. You can see predictions of the plate cooling model on the left for heat flow and bathymetry. It matches the half space cooling predictions well at young ages, but then it flattens out at older ages, and so it does a better job fitting the observations. A drawback of the plate cooling model is that it does not explain why an isothermal lower boundary exists. It does not provide a physical mechanism to supply extra heat to the base of the lithosphere. However, since seismic waves actually travel through the lithosphere, seismic models should be able to provide maybe better constraints on lithospheric evolution. But so far, they've reached conflicting conclusions. These are all shear velocity studies done in the Pacific Basin. On the upper right, Ritzwaller and co-authors showed that within the Pacific Basin, shear velocity increases with age according to the half-space cooling model until about 75 million years or so, and then it dips down. And they explain this flattening as reheating by small-scale convection. On the other hand, Maggie and others developed a tomography model for the Pacific that showed that shear velocity evolved with age as expected for half-space cooling, and they stated that they cannot detect the strong flattening that Ritzwaller did. Beneath that, Colleen Dalton also found good agreement between shear velocity in the Pacific and half-space cooling model geotherms, or isotherms, excuse me. On the lower right, Burgos inferred the base of the lithosphere from shear velocity in the Pacific and found better agreement with the plate cooling model than with half-space cooling. So still sort of an outstanding question here. All four of these examples that I'm showing here, the primary data set used to derive these models were the phase velocities of Rayleigh waves. This animation on the left shows the particle motion of a Rayleigh wave. It involves a component of shear and a component of compression. As a surface wave, it travels parallel to the surface of the Earth, but in the crust and in some cases in the mantle. In general, Rayleigh waves offer the best available constraints on the structure of the lithosphere, especially at global scales and also the regional scales like an ocean basin. And there are several reasons for this. Rayleigh waves are clear on the vertical component of seismograms. They're typically well separated from other seismic arrivals. They're well excited by shallow earthquakes. Their travel times are straightforward to measure, and they are well dispersed in frequency. And also important is their depth sensitivity. The curve on the left in the slide shows the sensitivity of Rayleigh wave phase velocity to VSV, the speed of vertically polarized, horizontally traveling shear waves. The curves are each normalized relative to their maximum value. And as is well known, longer periods sample deeper structure. This property is routinely utilized to solve for variations in VSV in the crust and then in the mantle to depths as great as 300 kilometers. The figures on the right show the sensitivity of Rayleigh wave phase velocity to the speeds of horizontally and vertically traveling P waves and also density. They're normalized by the same factor as on the left. And one of the challenges of working with Rayleigh wave phase velocity is that these other sensitivities, while not as large as the VSV sensitivity, are also not zero or entirely negligible either. So when solving for shear wave speed, most studies impose assumptions about how VP and density scale to VS. A direction that holds some promise is to incorporate other Rayleigh wave observables. And two such options are one, Rayleigh wave ellipticity, also referred to as the HV ratio, which measures the ratio of Rayleigh wave amplitude on the horizontal and vertical components. The second is local site amplification. One advantage of considering these other observables is that their sensitivity to elastic structure, oh, I don't know why that forwarded on its own. One advantage to considering these other observables is that their sensitivity to elastic structure complements that of phase velocity, which I'll show later in this presentation. And another advantage is that ellipticity and amplification are local scale observables. They're mainly sensitive to elastic structure right at the station, unlike phase velocity, which is integrated along the path. Several studies have demonstrated the benefits of jointly inverting phase velocity and ellipticity. This is a figure on the left from a paper by Sanchi Lin and co-authors. They compare the results of 3 inversions. All 3 inversions invert phase velocity data and solve for variations in shear velocity. The second and third ones invert phase velocity data and ellipticity together. And the third one solves for density and VP-VS ratio in the upper crust in addition to VS. So you can see in the top that all 3 models fit the phase velocity data well, but the HV data are much better fit with lower density and a high VP-VS ratio in the shallow crust. which is shown by model 3. And then the maps on the right show shear velocity, and again, not sure why it's forwarding, shear velocity in the shallow crust, 0 to 3 kilometers depth in the Western US. And notice that the color scales differ. So the inclusion of ellipticity data and their constraints significantly changes the patterns and the anomaly strength. Model 3 shows much better agreement between low shear velocity and known sedimentary basins. And now several groups routinely invert both phase velocity and ellipticity to solve for regional scale tomographic models. Local site amplification, in contrast, is typically measured using one of two approaches. Bowden et al. On the left applied wavefront tracking to ambient noise cross correlations to measure amplification. In this figure, they provide a comparison to predictions made using an existing 3D seismic model for North America from Schmant et al. The comparisons show reasonably good agreement on the large scale features, but also show that it may be possible to add new information about the crust and the upper mantle by incorporating new constraints from amplification. At longer periods, Eddy and Ekstrom measured relative amplification from the ratio of Rayleigh wave amplitudes at nearby stations. They find stronger and rougher anomalies at shorter periods compared to long periods, and reasonably good agreement between amplification anomalies and known tectonic structures like around the Colorado Plateau and the Snake River Plain. The bottom panels show predicted amplification using a 3D global mantle model overlain by crust 2.0. And again, agreement with the observations is reasonably good on the large scale structures, but the observations contain stronger and shorter wavelength features that hint at an opportunity to improve seismic models. To the best of my knowledge, only one study has utilized local site amplification in an inversion for depth-dependent seismic structure. Louis Chardon and co-authors determined amplification in the Western US using the amplitude ratio approach developed by Eddy and Ekstrom. And then they applied a Monte Carlo approach to solve for perturbations in shear wave speed. It's worth emphasizing that they used only amplification data in building this model, so it's a nice test of what can be constrained by amplification alone. And this figure has a lot going on, but I've tried to highlight the left column, which is their amplification derived model that they're then comparing to a number of other US array models. So I would say the amplification model agrees better with the other models at 60 and 100 kilometers depths than it does at greater depths, but it captures the north-south contrast in wave speed at all depths shown here. So in my group, we're interested in developing an approach to jointly invert Rayleigh wave amplification and phase velocity to constrain elastic structure. The top equation here linear relates a phase velocity anomaly at frequency omega to perturbations in several depth-dependent model parameters, VSV, VPV, VPH, and density. The phase velocity sensitivity kernels are denoted by the capital K functions, and they depend on both depth and frequency. So perturbation theory allows this linear relationship to be valid under certain circumstances, certain assumptions, and it also allows the phase velocity kernels to be calculated analytically from the eigenfunctions of a reference model. And this equation is widely utilized in seismology. Now below it, I plotted an analogous equation for amplification, linear relating the log of an amplification ratio to perturbations in the same model parameters. However, we need to understand to what extent this linear relationship is valid. Moreover, amplification kernels cannot be calculated analytically and they must be determined numerically. So this motivates the first stage of our amplification study, understanding amplification sensitivity. In particular, we are interested in obtaining amplification sensitivity to the 4 model parameters and also comparing it to phase velocity sensitivities. We can explore the extent to which the sensitivity depends on the reference model, as well as depends on the size of the perturbations. And we can also test the validity of the linear relationship. So the next few slides will explore that. Here we're considering 3 different reference Earth models, 2 that have the same simple mantle structure, but different crustal thicknesses, 36 and 56 kilometers, and 1 that is completely different. For each model, we perturb a single model parameter by the same relative amount while keeping all parameters fixed. And we try both a positive 5% perturbation and a negative 3% perturbation in 2 kilometer thick layers. We run the normal mode code Minios on every perturbed model file and then determine amplification and phase velocity from the Minios output. Amplification, as you can see in the bottom, can be calculated from the group velocity and the radial eigenfunctions evaluated at the receiver location. So these figures that just popped up are the numerical sensitivities for amplification for the 3 reference models and the 2 perturbation types at different periods, all normalized to a plus 1% model perturbation. And interestingly, the calculations show essentially no dependence on the perturbation size. We get the same normalized sensitivity for both the +5 and -3% perturbations, and then a mild sensitivity to the reference model. More so at short periods where presumably the much slower velocities in the crust in model 3 have an impact on the predicted amplification. Importantly, however, the shape of the kernels and the depth range of the maximum sensitivity are consistent between the 6 calculations. So the next few slides will focus on the sensitivities from the reference model that has the 36 kilometer thick crust. And I should point out that this type of numerical calculation for the depth sensitivity of amplification has been shown by others, but here we've explored its dependence on the model and the perturbation size in new detail. So this slide compares the amplification and phase velocity sensitivities, now focusing on the VSV, VPV, and VPH sensitivities. And there's 3 main points I want to make here. First, the sensitivity of amplification to these parameters is not so different from the sensitivity of phase velocity. The 2 sets of kernels have pretty similar shapes, and the depth of peak sensitivity increases with period for both. Second, however, the depth of peak sensitivity for amplification is slightly shallower than for phase velocity at a given period. For example, at 40 seconds on the right, the peak is at around 40 or 50 kilometers for amplification versus 60 or 70 kilometers for phase velocity. And third, amplification is more sensitive to VPV and VPH than phase velocity is. The phase velocity sensitivity to VPV and VPH is almost always less than half the sensitivity to VSV, but for amplification, it can be comparable. Here's another perspective on the relative sensitivities of amplification and phase velocity to different model parameters. We perturb each model parameter by -5% in the depth range 70 to 100 kilometers, while keeping all other parameters fixed. And as we saw on the previous slide, VSV has a larger effect on both amplification and phase velocity than the other model parameters. However, the relative importance of VPV, VPH, and density is bigger for amplification than it is for phase velocity. We did another set of calculations to understand how the amplification and phase velocity sensitivities complement each other. We systematically varied both MOHO depth and shear wave speed in the lithosphere. Here I'm comparing amplification and phase velocity predictions for 3 MOHO depths, 28, 36, and 44 kilometers, and 3 values for lithospheric thickness, 4.2, 4.5, and 4.8 kilometers per second. And I said lithospheric thickness, but I meant lithospheric shear velocity. All predictions are shown relative to a MOHO of 36 kilometers and lithospheric VS of 4.5. The phase velocities on the right show a dominant control by lithospheric VS. The blue, green, and red curves are really well separated from each other at all periods greater than 35 seconds. And the effect of the crust only really becomes important at shorter periods. However, the amplification calculations on the left show a much larger influence of MOHO depth. At periods less than 40 seconds, MOHO is actually the first order control on amplification, with the deeper 44 kilometer MOHO causing amplification and the shallower 28 kilometer MOHO causing de-amplification. For 40 to 80 seconds, both MOHO depth and lithospheric VS contribute at similar levels. And then at the longest periods, lithospheric VS is what's dominant. So to sort of summarize this discussion of amplification sensitivity, the phase velocity and amplification sensitivities to elastic structure are complementary in that their dependence on depth and period have a lot of overlap. However, compared to phase velocity, amplification is more sensitive to P wave speed and also to the properties of the crust. So we view this as an opportunity to use the 2 sets of observations together to obtain new constraints on the seismic structure of the lithosphere. And we've been developing a joint inversion approach and with the goal of applying it to Alaska, in particular to take advantage of the excellent station coverage in Alaska because of the Earthscope transportable array there. Alaska is an interesting target because it is so geologically and tectonically diverse. Its southern perimeter is dominated by subduction of the normal Pacific plate in the west and of the thickened Yakutat terrain in the east, with volcanism actively occurring along the Aleutian Arc, which you can see by the pink triangles. Volcanism is absent in the Denali volcanic gap, which overlaps in space with the outline of the subducted Yakutat terrain. And then much farther north, topography is dominated by the Brooks Range, which has been interpreted by previous studies to be underlain by thick lithosphere. The Colville Basin is a broad sedimentary basin that is up to 10 kilometers thick in places. So we've measured Rayleigh wave amplitude and travel time from 318 shallow teleseismic earthquakes at 248 Earthscope stations. We used the automated surface wave measuring system of Ginn and Garrity at 10 periods between 10 and 140 seconds. And to estimate amplification, we follow the amplitude ratio approach of Eddy and Ekstrom. I'm going to sort of briefly cover it here. So an amplitude from event K and station I has 4 contributions: excitation at the earthquake source, local structure at the receiver, focusing and attenuation during propagation. So we form the ratio of amplitudes at 2 adjacent stations I and J for event K. And the advantage of this is that the wave field has similar contributions from the source and propagation at these 2 stations. So the main contribution to the ratio will be the local structure at the receiver. And then for this ratio for the pair IJ is calculated for as many earthquakes as possible. And then for each pair, we combine those individual ratios to obtain a single value. We've experimented with several different ways of combining the individual measurements, including means and medians, and we ultimately prefer weighted mean of the log of the ratios that accounts for the non-uniform azimuthal coverage of our paths. And then finally, we use least squares inversion to solve for amplification at each station. These are by necessity relative amplifications, and so we set a reference station by forcing its amplification to be 1. Before I show the results for Alaska, I'll first show a set of predictions. We used the 3D shear velocity model for Alaska developed by Elizabeth Berg and co-authors, which was determined from Rayleigh wave phase velocities and ellipticities in a broad period range, as well as PS receiver functions. So we expect that it resolves crustal and mantle structure quite well. We sampled the model at every station location and then predicted amplification from the velocity profile at each station using Minios, and we formed relative amplification factors using the same reference stations that we do for the data. So you can see the predicted amplifications on the right here. Note the different color scales for the top and bottom panels. You can see how the slow velocities at shallow depths in the Brooks Range and Colville Basin in the north cause amplification at short periods, and how the fast velocities in those same areas at 100 kilometers depth are related to de-amplification in the predictions at longer periods. Now here I'm comparing our measured amplification with the predictions of the Berg model. So note the observed versus predicted labels in the panels, and also note the different color scales. Overall agreement is good, I would say. At 20 and 40 seconds on the left, the predictions match the observed amplification in the north, as pointed out on the previous slide, and also in the south along the volcanic arc, although here we find that the observations have stronger amplification than the predictions. At longer periods, 80 and 120 seconds on the right, the amplification in the north that bends around to the east has a similar magnitude in the observations and predictions. The main difference is at 80 seconds and 120 seconds. The main difference is in southwestern Alaska, where we measure the strongest amplification at these periods. It's also an area of amplification in the predictions, but much weaker than we observe. So overall, these comparisons suggest that the amplification observations are able to capture the main structural variations in Alaska. And furthermore, the differences between the observations and the predictions hint at opportunities to refine velocity models derived from phase velocity and ellipticity. For example, consider the band of amplification in northernmost Alaska at short periods. It is present in the observations and predictions, but its character differs. At 40 seconds, or between 20 and 40 seconds, the band shifts south in the observations, but not in the predictions. So this may suggest that amplification could slightly refine the depth dependence of shear and perhaps even compressional speed in the region. So to conclude this first section, we've shown that the sensitivities of phase velocity and amplification to elastic structure are complementary in that their dependence on depth and period has a lot of overlap. But compared to phase velocity, amplification is more sensitive to P wave speed and also to the properties of the crust. We've used the amplitude ratio approach in Alaska to measure relative amplification at 248 stations. And these new data agree well with predictions from an existing 3D shear velocity model, but there are some differences between the observations and predictions that suggest new opportunities to refine these models. So we're currently developing an approach to jointly invert phase velocity and amplification in Alaska and also in the contiguous 48 states for depth-dependent models of shear wave speed and compressional wave speed. I'll just pause for a second to take a sip of water, but also if anyone had a question, you feel free to chime in.
Yeah, I have a question. When you do the relative amplification, is there a reference station for this? Or I don't understand how the relative amplification sort of propagate around the model over an area if you're looking at very close stations.
Yeah, exactly. No, we have no constraint on absolute amplification. We only have constraint on relative amplification, and mainly the constraint is on relative amplification between nearby stations. So we've experimented with a couple of different ways of handling this. One is exactly what you said, which is we just set a reference station, choose a reference station, maybe in the middle of the array, and force that the reference station has the amplification of 1, and then all the other stations get determined relative to that. We have also experimented with just requiring that the log amplification for the whole area sums to 0, and that gives an identical result, other than sometimes there's a DC shift between stations. But I think it's one of the trickier things about doing this, because ultimately what we want to be able to do is use it to solve for elastic structure. That's what we're developing an approach to do now. And so the most promising approach for that seems to be to choose a reference station where we feel like the existing constraints on elastic structure are already really good. And so to maybe assume that there's one station where we quote unquote know what the velocity model is and use that as reference, and then everything else can be determined relative to that. But it's a good point. We don't have constraints on absolute amplification.
So another question that's related to that is, some years ago when I had one of my students look at so the gradiometry of surface waves across the US array, there were lots of bands of amplitude increases and decreases depending on the azimuth of approach of a particular Rayleigh wave. It seemed like focusing and defocusing was very important and related to the velocity structure in some way. I mean, the old way of looking at surface wave refraction, lateral refraction, is to look at the variation of phase velocity. And that naturally gives you focusing and defocusing. So how much scatter occurred in those amplitude ratios for, considering the events from different directions?
Yes, yeah, that's a great point. So for sure, when we look at amplitudes across an array for a single event, and I think my next slide might even show this. Okay, so here's an example. These are synthetic amplitudes generated with a 3D velocity model, but they're not so different than real amplitudes. And you can see that these Rayleigh wave amplitudes measured at US array stations do have banding. And in particular, I think you were talking about the banding that is parallel to the direction of propagation. And exactly, that's typically interpreted to be focusing and defocusing, that when waves travel through a low velocity channel, they get refracted in towards each other horizontally. and focused, and through a high velocity channel, they get defocused. So that's probably actually the dominant signal in the amplitudes that we observe at these periods is due to focusing and defocusing effects. So partly when we form these amplitude ratios, we assume we use nearby stations so that we can hope that the propagation effects like focusing and attenuation are similar for that part of the wave field, and so it's more or less canceled out. But of course, it's really not perfectly canceled out for the reasons that you mentioned, and so that's why we have a requirement of at least, we try to require at least 100 events per station pair, and then we do some weighting by azimuth to try to average out the fact and capture, so that so that effect is really being suppressed in doing that. And there is a fair amount of scatter at the same time when you look at comparisons like these between the observations and the predictions. The fact that the agreement is reasonably good, I think that suggests that the approach works fairly well if you have a large enough amount of data. I don't know if that quite answers the question. But actually, it's a great transition to what I wanted to talk about next. And I'm being mindful of the time here, but I'll try to do the next part in 10 minutes or so. As I mentioned, we see Rayleigh wave amplification as an opportunity, a somewhat underutilized data set that can provide new constraints on elastic structure. But we've also recently recognized the challenge of working with Rayleigh waves, especially array-based measurements of Rayleigh waves like at US Array. So I'll talk about that for the rest of my time. And this is work that's primarily been done by Anant Hariharan, a grad student in my group. We first started noticing this challenge when we were trying to make measurements of Rayleigh wave amplitude on synthetic waveforms calculated using the spectral element code SpecFEM 3D globe with a 3D seismic model. A big advantage of these synthetic calculations is that we can have a larger swath of the Earth covered with stations at the same time. For example, the entire 48 states, as you're seeing here, rather than the more limited dimensions of the actual US Array deployment. So these figures show 100-second Rayleigh wave amplitudes generated by an event at 42 kilometers depth in the northern Molucca Sea. And as I mentioned earlier, Rayleigh wave amplitudes are controlled by a few different factors: or the excitation at the source, the receiver structure, focusing, and attenuation during propagation. So the amplitudes that you're seeing here primarily reflect a combination of these factors, but they also contain something that we didn't expect, which are these alternating bands of high and low amplitude. The black arrow shows the direction of propagation, and you can see that the bands are perpendicular to the general direction of wave propagation. So they're roughly aligned with the wave fronts. And we initially thought this was an issue with the measurement method we were making. So we repeated our measurements using a second measurement method, but we found that the banding persisted regardless of which method we used. The amplitudes on the left were measured with the interstation approach of Jin and Garrity, and on the right with the phase match filtering approach of Uran Ekstrom. The banding could also be seen in travel times or Rayleigh wave phase delay times, especially when they're plotted as residuals relative to the predictions of a 1D model like PREM, which is what's shown here. So in these measurements, there's large scale variations in time that presumably result from the Rayleigh waves traveling through fast and slow regions and getting sped up and delayed. But then superimposed to that are these bands that I hope you can see that are again kind of parallel to aligned with the wave fronts, perpendicular to the direction of travel. And these are advances in delays, these bands of 5 to 10 seconds. 5 to 10 seconds is not a huge error for a total time delay integrated along a long propagation path. So it's unlikely to have a major effect on global phase velocity maps, for example, but that can be a really large effect for phase velocities estimated using nearby stations. For example, the two-station method or an array-based method like wavefront tracking, because those methods rely on differences in travel time over short distances. And so a few seconds can have a really big effect under those circumstances. And we found this when we calculated phase velocity maps from these synthetic amplitudes using the Eikonal equation. So these are phase velocity maps from a single event. And the input structure that we would ideally recover is shown in the bottom here. That's the input, that's the model that was used to generate these synthetic seismograms with the low velocity Western US and then a fast velocity craton in the north. But the recovered models are shown in the top. And in this case, the that banding in the travel times maps into really profound changes in phase velocity that overprint the structure that we're looking to recover. Here's a second example from a different event, again with two different measurement approaches. This is now a third measurement approach that I'm showing you. On the travel times on the left were measured using interstation crust correlation, and on the right using a cluster analysis method developed by Jitu Ma. And in this case, it's interesting, the banding is less severe and the input structure is better recovered, with the exception of the easternmost US at epicentral distances beyond 128 degrees or so. The bottom panel shows a transect along a ray path, which makes it possible to estimate the wavelength of the oscillation, which is around 3 to 5 degrees, depending on location. So long story short, we eventually figured out that the banding is interference from higher mode or overtone Rayleigh waves with the fundamental mode Rayleigh wave, but it's kind of in an unexpected way. So this record section in the middle here, the fundamental mode Rayleigh waves are shown in red with the R1 label for the minor arc and the R2 label for the major arc. And then the higher mode Rayleigh waves are shown in black. They're exaggerated by a factor of 5, so you can really see them with the X1 and X2 labels for the minor and major arc. Since the overtones travel at a fast group speed, they arrive much earlier than the fundamental mode. X1 arrives earlier than R1. So there's no interference. However, we found that at distances beyond 120 degrees or so, the overtone traveling on the major arc, X2, arrives in the same time window as the fundamental mode traveling on the minor arc, R1. That's what we're trying to isolate and measure. So we eventually realized that that's what we were observing with this banding, is the overtone on the major arc arriving in the same time window as the fundamental mode on the minor arc. And you can also see it on the right, where we plotted predicted group arrival times of the fundamental mode in the first 3 overtones. And at about 140 degrees, the second and third overtones are predicted to arrive at the same time as the fundamental mode. So we tested this idea using synthetic seismograms, but now calculated with normal mode summation for a 1D Earth model. The advantage of normal mode summation for synthetic seismograms is that we can control which mode branches are included in the seismograms. So we generated 2 sets, one set of seismograms that have only the fundamental mode and another set that have all the modes. And we measure the amplitudes and the travel times for both. And you can see the resulting phase velocity maps here. On the left is the input structure that we expect to recover. It's homogeneous since this is a 1D Earth model. And then the phase velocity maps determined from synthetic seismograms that contain only the fundamental mode shown in the middle, the recovery is pretty good. But the synthetic seismograms that contain all the modes, that phase velocity map that we recover is shown on the right. And it has these strong wavefront parallel bands of high and low velocity, just like the previous slide. So this was essentially confirmation that the banding that we are observing is due to the overtones interfering with the fundamental mode. So can we find evidence that this is happening in real data? Because so far everything I've shown you has been for synthetic seismograms. And the answer is yes. Here I'm showing Rayleigh wave phase velocity maps and amplitudes measured at US array stations for 2 events in 2012. You can see the direction of propagation and also the approximate wave fronts. And as with the synthetic data, there is this banding in phase velocity and also in amplitude that's similar to what I showed you from the synthetic data. Of course, these are just single events, and structural phase velocity maps are determined from many events. And one way to create structural phase velocity maps is to average many event-specific phase velocity maps, like the one I'm showing here, to create a composite. So on this slide, I'm showing how the higher mode interference can impact these composite maps. There's 3 things going on here. In the top left is a phase velocity map for 100-second Rayleigh waves that's determined from 549 events in our US array data set. Again, this is real data. The map in the bottom left is determined from events at distances less than 115 degrees, where our tests suggest that this higher mode interference should be less important. And then the bottom right are events greater than 115 degrees, where we think the interference effect should be largest. And we use the same number of events in both distance ranges to make the comparison make sense. And so you can see that the map determined from data at the greatest distances is much noisier than the other two maps and has relatively poor agreement with the map determined from all events. On the other hand, the map determined from all events does not seem to be unreasonably biased by the fact that it includes some data that we think are biased by overtone interference. So this is kind of good news that the inclusion of these biased data does not seem to have significantly deteriorated the quality of these phase velocity maps. So when Anant wrote his first paper about this phenomenon, we recommended that what researchers should do is just eliminate Rayleigh wave data from their data sets for events beyond 120 degrees, since that was the distance range that seemed most strongly impacted by this overtone interference. However, this blanket criterion was kind of unsatisfying because it means throwing out a lot of data, and it may remove some events or some data that are actually not low quality, and it may also end up including some data that should have been eliminated. So the work that Anant's been doing since then has been to sort of better understand this overtone interference. And I'm really not going to have time to show you my last few slides. I'm sorry about that, but let me at least spend 2 or 3 minutes just motivating it. So in reality, what we discovered, which I think many other people also knew, was that there's 2 principal factors that govern whether the higher modes will interfere with the fundamental mode. The first is the group arrival time. As we've seen, when the overtones arrive in the same time window as the fundamental mode, the interference can happen. And this is a well-known issue for love waves, since the group velocity of the first and second overtone are very close to the group velocity of the fundamental mode. You can see that in this top panel on the left here. And as you can see in the love wave record section in the middle, the overtones and the fundamental mode are traveling nearly together throughout the entire distance range. That makes it very difficult to isolate the fundamental mode and measure it. For Rayleigh waves in the bottom panel on the left, the group velocities of the fundamental mode and overtones are pretty well separated, especially at longer periods. But an underappreciated consequence of the good separation is that the overtones can get so far ahead of the fundamental mode that they intersect it on the major arc, as I already showed you. But the first factor is the group arrival time. And the second factor is the amount of excitation at the earthquake source. So in the best case scenario, the earthquake actually poorly excites the overtones. And so then they don't have much energy, they won't have a very strong signal on the seismogram, and they don't cause much interference with the fundamental mode. The figure here illustrates, this is for love waves at a few different periods and 2 different types of fault geometries, a 45-degree dip slip fault and a vertical dip slip fault. And so the dashed line is the excitation of the fundamental mode, and the solid line is the excitation of the first overtone at different source depths. And you can see that for the vertical dip slip geometry on the right, the first overtone is almost always more strongly excited than the fundamental mode, regardless of source depth. However, for the 45-degree dip slip fault, the amount of excitation changes strongly with source depth. At shallow depths, the first overtone is about as strongly excited as the fundamental mode, if not slightly more excited. However, at around 150 kilometers, the first overtone is weakly excited by the earthquake. And so earthquakes happening in this depth range might actually represent a data set with the possibility to isolate the fundamental mode well from interfering overtones, since the overtones are so poorly excited. So the slides that I won't have time to show you just kind of show some tests with normal mode seismograms that demonstrate that this is largely correct, that by considering the group velocity separation and also the relative excitation of overtones and the fundamental mode by the earthquake source, there's the potential exists to be able to target the data that we think will be most biased and remove them from our data sets while retaining all the data that we think would be high quality. So I will just go straight to my conclusions for this part. Overtone interference represents a challenge for both Rayleigh and love wave phase velocity measurements. And the Rayleigh wave interference was previously not well recognized. Major arc interference for Rayleigh waves and minor arc interference for love wave patterns are well explained by considering the excitation of overtones relative to the excitation of the fundamental mode, and the group velocity separation also matters. And we see new opportunities for quality control, for improving the quality of our love wave and Rayleigh wave phase velocity maps. We can eliminate data with large overtone excitation and also closely spaced group velocities, while keeping some data that has been traditionally been excluded. For example, data from intermediate depth earthquakes, depending on the fault geometry, may actually provide valuable measurements for surface waves. So I will stop there. Let's see, there we go. And thanks for your time. Sorry to go a little bit over, but I'd be happy to take any questions.
Well, I'll go again. I enjoyed your talk quite a bit because I'm fascinated by surface waves. And one way, I'm not sure if this is possible or not, but if you have an array, you can do some frequency wave number analysis of it and remove or get rid of the back propagating wave by filtering in the wave number domain. Do you think that's possible for like even US array? I haven't looked at the problem. I don't. Maybe you've done that.
Yeah, I think I haven't tried it, but I know other people have tried something like that, especially for love waves, to try to because the love wave overtones might have a similar group velocity as the fundamental mode, but they have very different phase velocities from the fundamental mode. So there are properties of the overtones that, yeah, when plotted in the right space, show up differently from the fundamental mode. So there have been studies that have tried to do that for US array, at least the ones that I'm aware of. One of the tricky things is that the interference patterns really require a certain epicentral distance range to be able to see it pretty clearly. And so it requires kind of grouping together portions of the US array stations, and that degrades the lateral resolution somewhat by being by needing to do that. But yeah, there certainly are some papers that have tried to do that. On the other hand, to the best of my knowledge, there really aren't many love wave phase velocity maps for US array. There's many different groups of Rayleigh wave phase velocity maps for US array, and they're very high quality, and we've learned a lot from them, but there's not much of an equivalent for Rayleigh waves, I think, because of these challenges.
Well, I think that was a very interesting talk. I guess a lot of people are still thinking about it. Could you maybe tell us a little bit about the tests that you performed a little bit more? I know you said you never had a lot of time, but maybe we can just like look at those a little bit and just see your results for that.
Oh yeah, sure. That's a good idea. If people don't mind sticking around for a couple minutes. Let's see. So what was I going to say about that? Let me share. All right, so I won't spend too much time on this, but I was going to say that to understand the tests that we did, these are with normal mode synthetics. I wanted to introduce two new parameters. One is called the excitation ratio, which is just the ratio of the source excitation of the overtone to that of the fundamental mode. And you can see in the bottom panel here, I've plotted the excitation ratio for love waves for a 45-degree dip slip fault with different source depths, and also for a vertical dip slip fault at different source depths. And when this excitation ratio is large, it suggests there's a high risk of overtone interfering with the fundamental mode. And then the second parameter is how we characterize the interference, which we call an amplitude interference pattern. Essentially, for every test that we did, we generated two sets of synthetic seismograms. One set that contained only the fundamental modes, and another set that contained all the modes. And in the top panel here, you can see 100-second Rayleigh wave amplitudes from the seismograms that contain only the fundamental mode. as a function of distance. And then the middle, the same measurements, but from the seismograms that contain all the modes. So the two sets of amplitude measurements are very similar, but they are a tiny bit different. And the bottom panel is how we quantify that difference. We just take the ratio of the middle one to the top one. And if the amplitudes are the same, then that value should be 1 at all distances. And any departures from 1 represent the impact that all the modes have versus when just the fundamental mode is present. So in this particular case, the main thing that I think should stick out to you is that these greater epicentral distances, the ratio of the two can be as small as 0.8 or as large as 1.2. And we interpret this to be the overtones on the major arc interfering with the fundamental mode on the minor arc. And so the test that I would have shown you, essentially, we calculate synthetic seismograms and calculate interference patterns for earthquakes of different geometries and different depths. So varying how strongly the overtones are excited relative to the fundamental mode. And then we look at how that impacts the amplitude measurements, the fundamental measurements that we're ultimately trying to measure. And maybe I'll just show this one figure and then I can stop. But this is for a strike slip earthquake. These are 75-second amplitude measurements. And again, it's this interference pattern where I plot the amplitude of the measured from the all mode synthetic over that measured from the fundamental mode synthetic. And then we've done it for earthquakes at 4 different depths: 12, 62, 112, and 162 kilometers. And so you can see from the figure on the left that we might expect that the earthquakes at 112 and 162 kilometers, the overtone is poorly excited at 75 seconds period, whereas at shallow depths, the overtone is pretty well excited. And our synthetic seismograms confirm our intuition on that for the two events with shallow depths, the interference pattern is really quite strong for the love waves, that the overtone is really dominating the measurement that we're making. But at the two deeper earthquakes, because the overtone is poorly excited, the interference pattern is much closer to 1. So what I would have shown you is that for these tests we did with normal mode synthetic seismograms, we're able to confirm that really the excitation ratio of the overtone and also the group velocity separation are what's controlling the interference strength. And this is important because it's a pathway to data selection, that it would allow us, by being able to predict those quantities, to remove the data we think are affected while retaining the data that we think are minimally biased, and hopefully be able to improve our phase velocity maps as a result.
All right, thank you. So what all different types of faults did you test these results for? I saw a couple different, but can you have like a summary of which ones you used?
Yeah, in the paper, a non-tested strike slip fault, vertical dip slip fault, and a 45-degree dip slip fault, which spans a lot of the variety. And then I think in the revisions that we did in the response to the reviewer, he tested an additional other set of fault geometries. But the 3 that we mentioned in the paper, this paper is in GJI earlier this year, span the spectrum of behavior that we found from all of the subsequent tests.
Are there any other questions? If not, thank you so much for this great talk.
Well, thanks for the invitation. It was nice to see you all, and yeah, take care with the weather and stay healthy and all that.